Hello, this is part 3 of a 3-part lesson on geometric optics. In the previous lesson, we talked about lenses and image formation involving lenses, and in this lesson, we'll talk about mirrors and images formed from reflection off of mirrors. All the images that you see in this video are from OpenStax College Physics, distributed under the Creative Commons Attribution License version 4.0 by openstax.org. When you look at yourself in a mirror, a plane mirror, a flat mirror, do you see a real or a virtual image of yourself? Well, let's consider what's going on in this figure right here. We have a observer who is seeing an image of this bottle in the mirror. And from the observer's perspective, it looks like the rays of light that originated from the object and eventually made it to her eye originated along a path that came from behind the mirror. So the light that's traveling to the observer's eye in this example never actually came from the point where the light appears to come from. It only appears to come from the spot because the light rays obey the law of reflection and bounce off the mirror. So that makes this a virtual image. All images that you see in flat or plane mirrors are virtual images. But the image distance is exactly the same as the object distance. The distance the image appears to be behind the mirror is exactly the same as the distance from the mirror to the object. So let's take a look at what happens to rays of light when they reflect off of curved mirrors. And the first example we're going to look at is a mirror that is concave. So this figure is showing parallel rays that are traveling toward the surface of a concave mirror. Each of the rays, when it strikes the surface of the mirror, obeys the law of reflection. The angle of incidence relative to the normal line at that point is equal to the angle of reflection. But because the mirror's surface is curved, the rays are redirected toward a focal point that's located in front of the mirror. Now in the real world, circular mirrors, that's mirrors that have curvature, or should I say spherical mirrors, mirrors that have curvature can be thought of as a part of a sphere, will not redirect light from all points on their surface to exactly the same point in space. This is called spherical aberrations. But if the radius of curvature is sufficiently large, or in other words, the curvature is sufficiently small, all the rays that strike the mirror at all places will approximately converge at the same point called the focal point. So remember, this is very similar to what happens with spherical lenses. So we consider this an idealization, but it's an approximation that makes our life easier when we try to understand how mirrors behave when rays of light reflect off the surfaces of mirrors. So just like a lens, we can think of a spherical mirror as having a focal point, and the distance from the surface of the the surface of the mirror to this focal point is called the focal length, which we can represent with an F. So what kind of a mirror is this? Is this a converging or a diverging mirror? It's a converging mirror because the rays of light converge at the focal point, the same point in space. Now let's take a look at a convex mirror, a mirror that bulges out in the middle. A mirror like this is a diverging mirror because rays of light that approach the mirror parallel to one another at different points will be reflected in such a way that makes those rays diverge from one another after the reflection. They spread out and never converge. So if you're an observer looking at a diverging or convex mirror, like this, you're looking in this direction, From your perspective, those rays of light that reflected off the surface of this convex mirror will never converge in a real sense. But from your perspective, it looks like all of those rays followed a line that has them converging at a spot behind the lens. So convex or diverging mirrors also have a focal point, labeled capital F in this picture, and they also have a focal length, labeled little f in this picture. But I call this focal point and this focal length a virtual focal point because the light that the observer sees never actually came along a path that passed through that point. They only appear to have come from that point because of the reflections that have occurred. So, by convention, a diverging mirror has a focal length that is negative, less than 0. On the previous slide, the converging lens, or the converging mirror, or the concave mirror, has a positive focal length by convention. You see, this mirrors, pun intended, the situation for lenses. For diverging lenses, we have a negative focal length. For diverging mirrors, we have a negative focal length. For converging lenses and mirrors, we have a positive focal length. But be careful, a diverging mirror is convex. A diverging lens is concave. But both diverging mirrors and lenses have a negative focal length by convention. Like with lenses, we can understand image formation for light reflecting off of mirrors by drawing ray diagrams. And so this is a ray diagram for a converging mirror, and there's 3 principal rays drawn on this figure. Let's walk through them and note the similarities between these rays and the principal rays that we draw for ray diagrams involving lenses. All right, so the object is a key in this case. Let's consider light emanating from the top of the key, and 3 rays representing light traveling from this spot are labeled on this figure. Ray 1 is a ray of light that begins by traveling parallel to the optic axis, the black line in this figure. A ray that travels parallel to the optic axis will undergo reflection at the mirror in such a way that takes it through the focal point, like so. Now let's take a look at ray number 2. Ray number 2 is special because it leaves the object traveling along a path that's going to take it exactly to the center of the mirror. A ray that travels a path like this and goes exactly to the center of the mirror will undergo reflection and will obey the law of reflection, where the angle of the incoming ray relative to the optic axis is exactly the same as the angle of the reflected ray relative to the optic axis. This angle right here is exactly the same as that angle right there. All right, finally, let's consider ray number 3. Ray number 3 is essentially the opposite of ray number 1. Ray number 1 leaves parallel to the optic axis and reflects through the focal point. Ray number 3 travels through the focal point on its way to the mirror and reflects in such a way that it leaves the mirror parallel to the optic axis. Okay, so just like with lenses, the image of the spot on the key, the object, where these 3 rays originated, is going to be formed where those 3 rays converge in space. So right here. So if you're an observer looking back at the mirror, you will see an image of the key right here in space. You'll also see the actual key, the object, at the same time. Is this a real or a virtual image? So ask yourself, is the ray of light, are the rays of light actually converging at that point in space, or do they only appear to converge at that point in space because of the way the observer is looking at the mirror? And the answer is, this is a real image because those 3 rays actually converge at that point in space. Another way of saying this is that if I put a screen or a film, at that point in space, the image will be projected onto that screen. Let's draw a ray diagram for a convex mirror. So a convex mirror is a diverging mirror. It has a virtual focal point, which is located behind the lens. So I've drawn a convex mirror with an object represented by this arrow sitting in front of the mirror. I'll label it O. Now let's draw two of these principal rays and see where they intersect. You only need to draw two of the three to figure out where the image is formed. So let's start with ray number one, a ray that follows a rule like ray number one in the picture up here. This is a ray that leaves the object parallel to the optic axis, will reflect and travel along a path that takes it through the focal point. So a ray that leaves, let's use a different color, how about green? A ray that leaves the object traveling parallel to the optic axis will reflect in such a way that takes it along a path that goes to the focal point. Well, here, it can only go through the focal point in a virtual sense. It's going to reflect, it's a diverging lens. It's going to reflect and travel along a path like that. But if you're an observer, over here, looking back at the lens, from your perspective, it looks like this reflected ray originated along a path like this. It takes it through the focal point behind the lens. All right, now let's draw a ray that's analogous to ray 3 in the figure up here. That's a ray that goes through the focal point, will reflect and be parallel to the optic axis. So here, a ray leaving the object in my picture can travel along a path that takes it toward the focal point, like so, but it can never actually get to the focal point because it reaches the mirror first. And when it gets there, it's going to reflect and travel along a path parallel to the optic axis. So from this observer's perspective, those two rays never converge in a real sense, but in a virtual sense, they converge behind the lens at a spot right about here, which is where the object will appear. Is this a real or a virtual object? The answer is it's a virtual object, or sorry, image. It's a virtual image because from the observer's perspective, it looks like the light came from a spot behind the lens, but it didn't actually come from that spot. It only appears to come from that spot because of the reflections that have occurred. So this is a virtual image. Another way to think about virtual images is they can only be seen if the observer is looking at the mirror or looking at the lens. Virtual images cannot be projected onto screens or film. Just like with lenses, image formation involving mirrors can be parameterized using object distance, DO, image distance, DI, and focal length, little f. And just like the situation with lenses, the relationship between these quantities can be summarized using a mirror equation, which is given by this formula, which looks exactly the same as the lens equation. So mathematically, the mirror equation is exactly the same as the lens equation. And just like the lens equation, there's certain conventions we have to adopt and follow for the signs of these various quantities in order for the mirror equation to work out for us. Let me summarize them for you. First, let's look at focal length. For a converging or concave mirror, focal length by convention is greater than 0. It's positive. For a diverging mirror or convex mirror, focal length by convention is less than 0. So in the case of lenses and mirrors, converging lenses and mirrors have positive focal length. Diverging lenses and mirrors have negative focal length. For the situations that we'll encounter, object distance, DO, will always be a positive value because we are only considering single image formation involving single lenses or single mirrors. If you have more than one lens or mirror involved in some system for image formation, the situation can be more complicated. But for us, object distance will always be positive. Now, what about image distance? Just like the situation with lenses, if the image distance di is negative, less than 0, that indicates the image is virtual. If the image distance di is greater than 0, that indicates that the image is a real image. So let's end this lesson by considering something called lens power. If you have eyeglasses, your prescription is some form of lens power. And lens power is simply the reciprocal of focal length. Power equals 1 over f. But you gotta be careful because f has to be in meters. So when you see lens power, the units are given in something called a diopter, but a diopter is nothing special. A diopter is simply 1 over meters. All right. Let's finish up by demonstrating actual image formation using mirrors. So this is a convex mirror, a diverging mirror, and let's take a look at the image of the computer. Now my computer is a Surface Pro, and it's on the desk in front of me. It's recording me right now. Hold the mirror up, and you see an image of the Surface Pro on the desktop. Is this a real or a virtual image? Well, it's a virtual image. It appears, from my perspective, to be formed behind the surface of the mirror. Okay, now let's take a look at poles. All right, the next one is harder to show on video. This is a concave or a converging mirror. Let's look, so I gotta turn the mirror to face the camera, the computer, and if I hold the mirror sufficiently close to the camera, you see an upright, an upright, it's really funny looking, an upright virtual image of the computer. Actually, it looks like computers to infinity because you're seeing an image of an image of an image of an image of an image, right? But if I hold the mirror sufficiently far away from the computer and get things situated, where's my computer? There it is. Now I'm seeing an inverted real image of the computer. So for the converging mirror, much like the converging lens, the type of image that we see depends on the relationship between the object distance and the focal length. If the object distance is smaller than the focal length, you see an upright virtual image, but where is it? There it is. If the object distance is greater than the focal length, you see an inverted real image of the object. All right. We'll look at more demonstrations in class.